This is Unit 4, Waves. We're going to look at the fourth section, which is Wave Characteristics. We have the difference between a single pulse of energy, which is called, for example, a single ripple on the surface of a pond, or a single pulse on a slinky, and a continuous supply of energy, which would be basically a continuous wave or progressive wave. This can be demonstrated with the FET demo. Okay, a progressive wave transfers energy without the transfer of the medium. So there's no net motion of the medium, so the medium oscillates from side to side, but the energy travels from the start point to the finishing point. So the particles travel from side to side, but they go back to their original position again. And this is a demo that I can probably show you here. This is a transverse wave. The oscillation is in a lateral direction. Okay, let's try it again. The particles go up and down, but they stay in the same place. We'll try that again. And again. Up and down. The particles don't actually move. It's the energy, it's the wave that travels. Let's do the same for a longitudinal wave. There it is. The particles go from side to side and then back to the same position again. So the medium does not move. It moves but goes back to its original position again. The energy is transferred forward. Okay, here we go. There's energy moving that way, and you see the energy is moving that way, but the particles or the loops on the spring stay in the same place. Okay, here again we have the case of transverse and longitudinal waves. This is a longitudinal wave, basically because the particles oscillate in the same direction or are parallel to the direction of the flow of energy. The energy starts from the left and moves to the right. Okay, so the energy is going from left to right. However, the particles are also moving from left to right and right to left. If you look at one particular particle, let's choose this one, it actually oscillates around this fixed point and doesn't actually go anywhere. It ends up in the same place again. So even though it is moving, it goes back to its original position. There is no net transfer of the medium. So a sound wave, for example, is a longitudinal wave. The disturbance is parallel to the direction of the motion of the wave. So the energy is going that way, and the oscillations, the particles are oscillating parallel to the direction of the motion of the wave. Transverse wave, however, the energy is going from left to right, but the particles are oscillating at 90 degrees to that. They're going up and down. So this is called a transverse wave. So for example, light wave is a transverse wave where the disturbance in the medium is perpendicular to the direction of the motion of the wave. So the wave is going from left to right, but the disturbance is in the vertical plane. So the particles oscillate up and down. This idea of wavefronts and rays is a kind of easy to understand the basic idea, but difficult to define it. So I've just given you the definition of these two kind of aspects. The wavefront is basically the line. If I go to the pointer red, okay, this and this and this and this, nope, are all on the same wavefront. They're neighboring points and they're all in phase. Okay, this and this are not the same wavefront because they're not neighboring. They're not right next to each other. These particles are right next to each other, so they're part of the wavefront. The ray is the direction in which the energy is traveling, so this would be the ray. One interesting thing is that the ray is at 90 degrees, badly drawn here, is 90 degrees to the wavefront. Describe the terms crest, trough, compression and rarefaction. Okay, here we have a transverse wave. The top part of the wave is called the crest, Right, just get back to pointer options. The arrow, yes. The top part of the wave is called the crest. The bottom wave is called the trough. This is where the distance between the crest and the trough is twice the amplitude. Compression and rarefaction is in a longitudinal wave. Here we have areas of compression here and areas of rarefaction, which is areas of a low density. Compression is areas of high density. So the compression is where the particles are close together. The rarefaction is when they're furthest apart, the smallest density. Here's a longitudinal wave again. You can see that you basically see the line of compression moving from left to right. Same for rarefaction. This is a graph showing the density of air with distance. This is a high density, so that's a peak density. This is a minimum density, rarefaction, so that's low. That's peak, that's low. Define the terms displacement, amplitude, frequency, period, wave speed and intensity. These are fairly straightforward definitions that need to be learned. Displacement, the distance that an oscillation system is from its equilibrium position. The amplitude is the maximum displacement of an oscillating system from its equilibrium position. The frequency, this is the number of complete oscillations made by a system per second, or the number of oscillations made per second by a wave source. In terms of waves, it's that second aspect. Period, this is the time taken for one complete or single oscillation, or in terms of waves, it's the time taken for the source of the wave to make one oscillation. In other words, the time taken for one wave to get past a fixed point. The wave speed, this is the distance travelled by the wave per second. The intensity, this is basically the power output per unit area, and it's related to the amplitude, but not exactly. It's related to the amplitude squared. Okay, we have to draw and explain displacement time and displacement position graphs for transverse and longitudinal waves. The displacement position graph. Okay, this is the displacement, this is the position. The distance between one crest and another crest is called the wavelength, or from one trough to another trough. Okay, so this is how the displacement changes with distance. Another way of representing the graph is how the displacement changes at a particular point, how that displacement changes with time. Here again we have the amplitude, but since we have one particular point with time, it goes to the crest, to the peak. The time taken from one peak to the next peak is called the time period, and that's labelled here. So beware when you have to label either the wavelength or the time period, that you know whether it's a displacement position graph or a displacement time graph. This is a longitudinal wave, and this can be represented by a transverse sinusoidal pattern. This is the most common way of presenting this. The compression is here and here. The rarefaction is there. Now, if you notice, the first compression is when all these particles are moved to the right. These are moved to the right. These particles here move to the right. So we have a positive displacement here. Here, these particles are moved to the left, so we have a negative displacement here. And here again, these particles here are moving to the right, so we have a positive displacement. Okay, it's difficult to see this, but we have a clip which can make it a bit easier to show you. So, okay, we have to click on this. Here we go. Okay, this doesn't seem to be working. I will show you in the class how this is. Okay. Okay, next slide. Derive and apply the relationship between wave speed, wavelength and frequency. Okay, the best way to understand this is to define speed is the distance traveled per unit time. Now we're talking about a wave which is passing. So we can say, what is the time taken for one wave to pass? First of all, how long does it take for one wavelength to pass? Well, by definition, the time taken for one wave to pass is the time period. And when one wave passes, how far has that wave gone? Well, basically, it's the wavelength. So the speed, which is the distance, which is the wavelength, divided by the time period, is going to look like this. Now we know that the time period is equal to 1 over f. This is where we were up to. The speed is the distance divided by time. When one wavelength passes, it travels one wavelength divided by the time, but the time is 1 over f. So therefore we have the speed, which is lambda f. So in other words, v is equal to lambda f. This is called the wave equation, or one of the many, but this is called basically the wave equation. Now we have a question on the wave equation. We're given the frequency, which is 110 Hertz. The wavelength is 153 centimeters. What is the velocity of the wave on the screen? And then a wave in the ocean has a period of 10 seconds, a wavelength of 200 meters. Find the wave speed. These are very easy questions. You should do them without needing any help. I'll put on pause, or you should pause now and try the problem. And the answers are as follows. This is the solution to the first one. The second solution is there. Other questions. Question 1. Pause. The next section is about the electromagnetic spectrum. You need to know all the different parts of the electromagnetic spectrum and roughly what their wavelengths are. First important thing is the light. Visible light goes from 400 nanometers, which is a blue end, the short wavelength, to red, which is above 700 nanometers, yellow 600, blue, green 500 nanometers. These need to be learned. And this is the whole picture, going from radio waves, which is hundreds of meters, even thousands of meters, down to about 3 meters. Microwaves from about 3 meters to about 1 centimeter. Infrared about 1 centimeter down to the limit of the red, which is 700 nanometers, 800 nanometers. Ultraviolet beyond here. X-rays is overlapping here, which is what scale are we looking at here? 10 to the minus 10 meters, and gamma rays from about 10 to the minus 10 downwards, 3 times 10 to the minus 12, and so on. Okay, so you need to know these. The last point is the same speed in free space. They all travel at 3 times 10 to the 8 meters per second. You need to know that as well. So that's it. We'll stop there, and that's your lot.